All right, everyone. Thank you so much for joining us today. My name is Terry Martin. I am the Chief Geospatial Information Officer at the National Alliance for Public Safety GIS Foundation, and I am one of the co-chairs of the Climate and Community Resilience Committee bringing you this webinar today. The committee is, of course, a part of the Geospatial Professional Network, which is a community that unites emerging and experienced GIS professionals through top-tier education, networking, and career development. So I want to give just a couple of quick logistical items. So this is a webinar. You should be muted by default. If you have questions, please use the Q&A. Our speakers will try to monitor that throughout. If we have time, we'll address them at the end. This is being recorded and will get added to the YouTube playlist usually within a day. So if you're registered for the webinar, you'll get an email that it is ready to go. So today we have a very important topic and a slate of very prestigious speakers who are going to delve into recent pilot projects that have brought together experts from their respective agencies and organizations focused around the dangers of extreme heat and how maps and location data can improve disaster preparedness and response. So to say that we have a packed agenda would be a massive understatement. So I want to go ahead and hand it over to Alan Leidner with New York City's Geospatial Information Systems and Mapping Organization, who will be driving the conversation along with his colleagues that he will introduce along the way. So Alan, over to you.
Okay. Thank you, Terry. And thank you to GPN for allowing us the time to speak and to meet all of you. Just a brief introduction for myself. I am trained as an urban planner, but I got involved in GIS, a route probably followed by a number of people. Ultimately, I became the GIO of New York City, and there had the opportunity to be the director of the Emergency Mapping and Data Center following the 9/11 attack. And ever since then, I've been deeply engaged in disaster preparedness and response through GIS. And in particular, over the last 8 years or so, I've worked for the Open Geospatial Consortium on a number of initiatives. Especially the disaster pilots that they've been running, and had the opportunity to apply for one in the extreme heat area. Worked with a number of colleagues who I've known for years to assemble a team, the team you see before you now, who will be doing the presentation. We did a lot of research. We got paid nothing, basically, to do all this work. I don't think anyone whose face you see got 1 penny out of this. So this was gratis. This is what you can get when you don't pay. And we will be going through, we've been aware of the European deaths and the deaths in Chicago and Vancouver and other cities. And we felt that this was, and more deaths apparently from any disaster type occur from extreme heat. So we really wanted to look into this. So on that basis, I think we should get started with Dr. David Green, who agreed to be part of our team and who worked for NASA and NOAA for many years. And David, I'm going to give it to you to further your introduction and take us through your slides.
Thank you, Alan. If we could put up the slides. As Alan said, I was with NASA and NOAA leading programs on disaster risk reduction, preparedness, mitigation, and over the years, the whole kind of geospatial capability and support of OGC was a critical part of the activities. Can we find my first slide, please?
I think we're at the end of it.
Up to the top.
And you want to go to the third slide.
It's about the third slide. So introduction to the team. This was a team effort. So as we get to my next slide, keep going. You'll see here myself, Dean, AJ, Vandana. We're all presenting today. Alan helping put this story together. I'll kick off with a discussion of the aspects of climate and heat and some of the compounding issues associated, why this is a geospatial, both an opportunity and a challenge. If you look in the background there, you can see some of the deviations from mean, which is really the variations and the mapping of where and when. That is critical to understanding the heat science. But going beyond that, one of the things I pushed OGC and the geospatial community was really moving from just the science understanding to the application. And that's the storyline you're going to hear today, the profile of going from science through to applications to impact to what do we do next. So let's go to my next slide. So in the climate context, we have climate change and we have climate variation. These variations are leading to extremes in weather, and that includes the extreme in heat events. From the Open Geospatial Consortium perspective, we wanted to drive what we called a pilot study. What was the feasibility of bringing the data, the models, the transdisciplinary approach to see how we could observe, map, and understand where these changes were happening, when they were happening. And from this, the vision was, given a successful pilot, we could demonstrate how we could do this at scale. We could develop this kind of living laboratory where people could come together, understand how it affects workflows and decision-making, and build the capabilities of services and support for smarter, safer, and healthier urban areas. As you can see here, the projections of 2050, things are going to change. It's urgent that we get going on this now. So let's go to the next slide. So here's a projection of the changes just occurring over a couple of days this June 20th to the 24th. And you can see how dramatically these heat profiles are moving. They're spatially sensitive. And we know that underlying that, every community, jurisdiction, building, car, transportation hub are all being impacted in different ways, but spatially sensitive. And those shifts and those temperature variations have very different impacts to different stakeholders. And we're trying to put this collective story together. Next slide. So the urban heat island, you may be familiar with that term, but it really refers to this area where you've trapped heat, whether it's due to the natural variations, whether it's that climate change transitions, or certainly the human-made impact. A lot of the urban heat island I will describe as by design. It's our structures, our surfaces, our activities, the degree of vegetation or not, and the type of materials and surfaces we choose and the way we lay them out. These variations can be, say, 3 to 7 degrees, and that's enough to interfere with human health and public infrastructure, with the role and ability to have this kind of safe, sustainable environment. Next slide. There are geospatial tools that have been developed. Here's an example of a National League of Cities tool that actually looks at the urban heat effect coupled with how are we doing on tree canopies? What is that risk and resilience variation that is occurring? And so I don't want to give you the idea that there's no tools out there. In fact, there's a lot of data, information, tools, and knowledge. That's one of the punchlines of this whole story. The question is, how do we actually put it together? Next slide. So the urban heat island effect is the result of surface absorption of heat from the sun, the cooling effects that might be from the evaporation and the emissions that relieve from a city. But as we move into areas that have more vegetation and canopy, as we get to that urban-rural interface and then into the rural areas, we have different levels of absorption depending on the health and nature of the vegetation and the cooling effects that can be enhanced, and the groundwater part of the story as well. Next slide. These variations occur over the daytime, whether the changes are the urban interface, the urban heat in the atmosphere, or at the interface with the surfaces. And you can see the profiles vary through the day, and they also vary dramatically with that level of vegetation and the amount on density of that built environment. So we have a very spatial story and a spatial sensitivity. That also includes, thank you, going to internal, the exposed surfaces and how they affect us inside structures, whether those structures are inside buildings, inside cars, the nature of that outside, metal, asphalt, other materials. They heat up, they transmit inside. And so we've got an external spatial problem and a distribution of internal problems related. And next slide, please. Now, the way we design our infrastructure, our communities and cities, is that radiation and thermal comfort level. It varies with bad designs that restrict or constrain the airflow or the material selection to good designs, which really think through what is an integrated approach that includes that spatial knowledge of temperature variations, utility, right? Manufacturing or home use, transportation use. And what are the things that we actually building into it, not just building resilience as I put in quotes, the building being resilient and the people in it, but actually that aspect of designing smart building and smart design and smart investment. Next slide, please. So urban heat islands by design. Now we look at that profile across a community, if you will, residential, commercial, other businesses, a water body, and wind and weather. So these variations are within and across a city or an urban area. There is a spatial distribution of how it interacts with the natural vegetation, water, and soil, but also the directionality of the exposure or vulnerability of those buildings, of those systems, of those individuals. And what we want to goal here is to protect in a sustainable way that high value, whether it is the people in the community and where they are relative to their safety, comfort, and long-term viability, as well as the aspects of their livelihood and their lifelines. Next slide. So the scale of the problem across surfaces, again, depends on the materials. We often talk about albedo, which is that how does that radiation of the sun or other radiative effects impact the surface? We relatively say on a scale of 0 to 1. Does it reflect, whether it's white paint, or is it black asphalt and clothing that absorbs? Next slide, please. We can also talk to the civil engineers and the designers to say, how have we actually laid out our city? Where are those corridors? There's information and data that exists. On that morphology chart there, it starts with things like looking at Landsat satellite imagery, which gives you the big picture, and then street map, which gives you the layout of the streets, to actual building data. And you can continue to add information till finally you get that well-designed grid that has that integrated perspective of not just where buildings should be or where roads are, but also considers this, what will it do to the heat story? Next slide, please. So there are socioeconomic and political impacts here. And the geospatial capabilities that everyone on this call has interest in touches on all of these, whether it's the public and environmental health stresses, whether it's the energy grid and the infrastructure that might be affected by brownouts, or the downstream impacts of food storage or pharmaceuticals, the elevated greenhouse gas effects, those long-term effects of these emissions and where they continue to collect. There's also a water story. And how is that water distributed, whether from the sanitation systems to the rivers to the lakes that might be nearby? And collectively, the economic and business impacts, which underfund both the short-term viability of jobs and livelihoods to the long-term sustainability of the commercial and financial investments. Next slide. So you see that there's lots of roles for different communities in the geospatial family to come together. Again, on that surface aspect, we want to be able to say where and when is the radiative temperature changing and differing from what is a normal, understandable condition. Imagery, whether it's from satellites, whether it's from airborne cameras and tower cameras to drones, across the spectrum is very sensitive to different things. In the infrared, we can see images of hotspots and heat zones. In optical, we can see whether the power's on, the power's off, or we can see the viability of different populations in movement or active or road systems. So the surface phenomenon is observable, mappable, and interpretable. Next slide. In the atmospheric, it's similar, but now we have even further dimensions. So the atmospheric state, the land surface, and the trajectory across that area in space and time requires, again, the ability to take all of these well-known data sets, models, and tools that give us the environmental outlook across all dimensions, space and time, vertical and horizontal. And then on top of this, we're going to add population data, census blocks, property conditions, road and transportation, food and other systems to the story. A very Earth system approach to our geospatial in the context of urban heat deviations and extremes. Next slide, please. Again, the science behind this is really a budget issue. How much energy is coming into the Earth? Where is it going? And where is it being re-emitted, convected, controlled, or in some cases, as we're getting better at this, mitigated and adapted to? And that's the big picture. And again, our pilot demonstrated what's feasible and possible. And what we'll be going to through this story is how those with different parts of this budget story need to come together to develop the services and tools to continue to be able to adapt and mitigate. Next slide, please. Now, there are risks, and you're going to hear a lot today about those risks of heat-related mortality and morbidity, but it's to demographics as well, the respect of children, aged, those who are vulnerable or more exposed, those who have a history of sensitivity, as well as the associated, as we said before, these are communities that might be isolated. These may be communities anywhere on the planet that in some way have a relationship to each other, but are sensitive to the heat environment. Next slide, please. Part of approach to this that I like to talk to from this kind of sciencey perspective is enabling people to ask the questions they want to ask. That's where you as the geospatial community are the enablers. Not everyone is a scientist, an engineer, or a geospatial expert, but we need to be able to enable people to ask the questions they want. Where is that hotspot? Is it in the urban area, the urban-rural interface? Is it in my neighborhood? And when is it there? And is it there at the same time as vulnerable populations? Is it part of a seasonal story? Is it those who are maybe in the policy arena who need to understand the long-term commitments and barriers that might need to be removed in order to do smart design or smart governance to allow people to actually collaborate who need to collaborate? Next slide, please. So measuring the urban environment means heat, but also, as I said, water, electrical power, the communication systems, the vegetation. We have in situ monitoring for a lot of that, which also includes, by the way, citizen science. A lot of people contributing their own spatial data, validation, and information, but increasingly remote sensing. And remote sensing, since I came from NASA and NOAA, much of my career, includes things like satellite and airborne. Now, things like Landsat, EcoStress, a sensor on the space station, Sentinel from the Europeans. There's a host of different type of data, a Swiss Army knife, if you will, to ask and answer all these different types of questions. Much of that data, I want everyone to understand, is both open and available and free. A lot of the data is open in the sense that you may have to purchase it or have an agreement for research, but it's available. And then there is commercial data, and there is a lot of that. And one of the things I also want people to understand is federal agencies are buying commercial data for you and others to actually have free and available in order to do development, testing, and validation. Again, what might appear to be commercial, if you're developing services, tools, or research, you may be able to get that data for free by working through the agencies that are actually buying it for the purposes of development. Now, if it is then transitioned to operations, then there you engage in a commercial relationship. There are also satellites and observations that are stationary, that sit right above where there may be a high density of interest. New York corridor, those California or other parts of the planet. And then there are free flyers, those that fly around the world every day. And there are advantages and disadvantages of those. And let's go to the next slide and I'll start to talk about a bit of that. So as I said, there is geospatial data. Landsat is the land surface. It's been around for decades. It's high resolution, but it's kind of optical. Then VIIRS, the I stands for infrared. There are sensors out there that are looking just for the hot areas. There are sensors that are looking at fine scale vegetation, canopy, trees. And then there are not just data, but there are data derived products, the vegetative indices, surface indices, population integrated products. So you're not always talking as the pure scientist who wants just the raw data, but there are derived products, and it's good to know where those are and that they are available. Next slide. The radiation conditions that people can look at is very sensitive, as we said, to that thermal spectrum, where in the spectrum of infrared to visible to whatever, that it's sensitive to heat or sensitive to the water. But as you start to look through the atmosphere, it's also important to remember that there are some limitations, sensitivity to what type of vegetation and the color and variations, the water absorption that might require some corrections. Those are not trivial. And the other is that once you get into an urban area, how well can you see through the buildings and around the structures, because you may be looking at various angles and you have to put that kind of angular story, which can be really important because it can reveal new information by looking at different angles. Next slide. A couple of other considerations to think about. Data is not always there when you need it. A lot of the satellites, for example, go through a cycle throughout the day so they can see things maybe in the morning or in the afternoon or maybe not at night. But one of the things to remember, and this has also changed, is people used to rely on one or two satellites. There's hundreds now, and you can put them together into what we call an observatory to be able to tell that more complete story. Some of them are optical, which means they don't see through clouds. But just a month ago, US and India launched a infrared satellite that covers the Earth every couple of days. And the private sector, Earth Fire Alliance, the Canadian Sat, and various others are putting up philanthropic satellites now that can measure every 15 minutes. And so we're going to have a lot more of this information relevant to the heat story. And there are smarter sensors and automation that's also going on in towers, mobile vehicles, and on the ground. So next slide, please. With that, we can do urban heat intensity maps. That spatial distribution of where is the land most heated? Do we need to worry about it? What's the consequences going to be? Is it going to be water impacts, health risks at certain thresholds? Maybe it's wildfires, and maybe it is other aspects that should also inform our future planning or redesign. This is the role maybe with our geospatial analysts of like civil engineering and city planners and resilience officers. The next slide. Next slide reminds people that it's not just where, but it's where and when. So is it that diurnal day-night issue, or is it the seasonal variation? And this comes into play with those who are looking at geospatial knowledge for investment and anticipation of growth. Where is the community going to continue to grow? What is the demographic of the community? Is that community aging? Is that community being revitalized? So that's land cover, land use over time. Next slide. The other questions you might be asking is, can I use my geospatial not just to detect the problem, please not just to detect the problem, but to figure out where the actual solutions are. Urban greening and canopy design, where are those cooling areas and the right materials? So mapping, piloting, and planning is not enough, but it's got to lead all the way to our geospatial capability for implementation to adaptation and a sustainable approach. Next slide. So from a geospatial perspective, we've got the natural landscapes, we've got the urban materials and composition, we've got the layout, the morphology, the urban geometry of buildings, cities, people, workplace. We've got where is heat generated, whether it's from the sky or from heat plants or data centers or human activity on the ground. And then what is that directionality of things changing through the weather and the geography and topography of our landscape or the local water and bathymetry. So those coastal effects to inland communities, whether they're on the ocean or whether they're on rivers or they're on mountainsides. Next slide. So our future direction, as you've heard me say, it's really about bringing and connecting the dots, integrating the geospatial concepts in ways which we haven't done before, perhaps aided by AI and new machine learning and predictive and decision support tools. At the same time, new constellations of information from all spectral regimes, giving us a much more thorough worldly story. And just a reminder, taking advantage of open data and open science. And what open science is, it's more than just data. It means that you're actually opening up and sharing your algorithms and your tools and making your dashboards more standard or more integrated. Next slide. I'm just about done. So where do we go from here? A lot is known. We've done really well on the science understanding. We do have data tools and agents. We have models, and that means predictive capability. So we can ask, what was it like before? And what's the foresight of where it's going to be in the next 5 years or 10 years that might be needed by governance bodies, or what might be needed tomorrow for a rescue or a intervention. So what should we do? On this call, we've got 100 people or so, all representing different organizations and different perspectives. Perfect. So we have to collect our research together and partner. We have to include not just the research and the engineers and the technologists, but also the policymakers. It's really important to have that full stakeholder engagement. Historically, information, but also thinking about where we innovate to include the heat science, technology, and the knowledge going forward. We have collective interests in this. We also know that different urban areas and the associated communities, economies, and professions have interest. I'll remind you, this also now includes a lot of the philanthropies and agents who we haven't included in our storyline before. So we can develop a more robust and reliable way forward. We've done a pilot, and what I'm emphasizing here is the next step is to go beyond pilot to further demonstrate, and those who are on this webinar today may be anxious to participate with our team and others to demonstrate how it works in their jurisdiction, and eventually develop those more sustainable tools and approaches. I think that was the last slide. Thank you.
David, thank you so much. This is Al Leidner again. And you really present quite a vision of all the data and all the technologies that are now available that weren't in the past, coming together, creating a huge potential to getting on top of a disaster type like extreme heat, but also other kinds of disasters. Our next speaker is Dean Hines of Safe Software. And what he will show you is some of the ways that all this data and all this technology can be integrated so that you can go from analysis ready data to decision ready intelligence, where you can start to make decisions. And this is not just simply at the federal level. This is for how does every jurisdiction look at its own circumstances using these tools and these capabilities and figure out the best pathway for themselves. And I think Dean can show you, will be showing you some of the ways that that can happen. So Dean, take it away.
Sure. Yeah. Thanks a lot, Alan, and of course, David, Dr. Green, for taking us through some of the background on what is urban heat island effect and how can we both measure it, map it, and cope with its impacts. So my name is Dean Hintz. I'm with Safe Software. I'm a product manager for open standards. And I've also done a lot of work with Open Geospatial Consortium, OGC, over the years. And just as a quick background about who SAFE is, we're the makers of the FME data integration automation platform. So we have both authoring tools as well as tools for publishing services. Next slide. And I guess our kind of claim to fame is really data integration, where we can read and write almost any type of spatial data or even non-spatial tabular database, cloud-based data, including remote sensing. And so of course, I'm biased, but I kind of feel like this is a great platform for doing disaster modeling because there are so many disparate data formats out there. But the other thing I'll emphasize, I mean, the principles we're talking about, there's other platforms you can use to execute them on other GIS platforms, tools, and open source. So, and the other thing I'd emphasize is that, yeah, we're also supporting integration of AI, and we're present in about 130 countries, about 200,000 users. And we've been around about 30 years, but we've been an OGC partner for more than 20 of those. So next slide. So focusing in on the OGC disaster resilience pilot, climate disaster pilot from last year. So this is not just an isolated pilot. The OGC has kind of had the foresight to see that climate and disaster is obviously a massive impact on society, and it also is a great context for doing pilots because it involves integrating across many different types of disparate data, and it's a great way to utilize open standards to try to bridge some of those data gaps. And so while this pilot focused on extreme heat events, and we had some specific study areas like New York City, we've also done disaster pilots. We're currently working on another one right now on flooding, and we've done things like storms and landslides and other impacts. Next slide. So yeah, I'm not going to get into detail here. David really covered off the urban heat island effect. And I'll just say from the Canadian perspective, because we're based in Canada, near Vancouver, we lost between 600 and 700 people in one weekend from a heat wave where, people like to think of Vancouver as very mild weather, but we had a temperature in the low 40s, and a lot of people just don't have air conditioning, and there was probably even power outages on top of that, or limited access to ventilation. So yeah, that was one of our worst natural disasters in recent memory in that area. Next slide. So focusing in on New York City, our goal here was to provide both ARD, as Alan mentioned, analysis ready data, and also localized heat warnings. And so in order to do that, we surveyed a number of existing urban heat island data and models that are out there, and we looked at what some of the primary factors are and how can we leverage of currently available data sets to kind of bring together a model that helps us localize heat alerts and analysis data. Next slide. So this is just kind of what you could call the layer cake of the combined heat effects that David, he kind of alluded to this phenomena. So you might have a forecast for 100 degrees Fahrenheit. Something to keep in mind, the forecasts are based on what's called natural environment, or a lot of people refer to. So by definition, we tend to place weather stations that feed our forecasts in places that avoid artificial interference. And so maybe the weather station is part of the data that goes into that forecast comes from a weather station in the middle of Central Park, which avoids a lot of the urban heat effect. And so that forecast, which you can add to that, is an heat island effect might be 8 degrees. You add humidity and the heat index or the felt temperature, and before you know it, you're up to the effective felt temperature. And that's not just cosmetic, oh, I feel hot. That's the actual physiological effect of the temperature of above 130 degrees Fahrenheit, which for many people is quite hazardous. Next slide. And Ajay and HSR folks will get into more detail on that following my bit. So this is kind of a big picture of what our goal was for our contribution. We need more accurate extreme heat alerts for urban areas because currently a lot of the alerts are just focused on that initial forecast and not on the localized effects. Yeah, so existing alerts there may be exceptions to that, but by and large, most places I know of don't have those kind of localized alerts. So we're using FME to basically look at surface type and come up with estimates about albedo, et cetera, in order to look at the primary factors in order to localize that and produce both heat alerts and analysis-ready data for downstream processing. Next slide. So this is just a quick, it's more of a general approach that we think is useful. There's a lot of, as David mentioned, there's tons of data out there, both in terms of weather models, climate models, and other factors. The challenge there isn't so much just getting data, but it's integrating across those data so that you can build a synthesis and evaluate things like cumulative effects and also bring in factors, let's say, from IoT or citizen science in order to make things more real time. So yeah, the last point there, our goal is not just localized alerts and visualizations, but how can we help support cumulative analysis so that we can have an understanding of combined effects, as we often see in disasters, as well as support things like AI analytics. And the whole, ultimately, I think there's this concept of a digital twin. So we have a digital twin, not just for things like a building or a plant, but also for the local urban environment, urban digital twin. Next slide. So this is, I think, an important concept, and we've seen this in a number of different OGC pilots where a lot of the forecast data or climate projection data is quite coarse. You might have kilometer level, 2-kilometer pixels from a climate model output. So the challenge there is how do we downscale the effects of that locally? And so one thing we found, which seemed to be borne out just by local observation and in terms of how people experience heat in the city, is that if you can identify what are some of the key contributing factors to the hazard, in the case of heat, it's surface type would be one example. In the case of flooding, it might be the DEM. And so if you can use that, combine that with that low resolution forecast, you can actually essentially have a pan sharpening approach to provide higher resolution estimates of local impacts. And there's ways of calibrating that based on local observations. Next slide. Next. So this is just this is from Climate Central. They were an important source. If you can go back one slide, please. This was an important source of some of the initial data. Sorry, previous slide ×2. We jumped ahead a few. Yeah, that one. Yeah, so just looking at the determinants, I did want to focus in on this quickly. So obviously in the scope of a pilot at OGC, we can't model everything. So we looked at some of the primary contributors and we saw that both the land cover type and the cooling effects of greenery and water, that was sort of accounted for more than 50% of the drivers, but there's other drivers that we could take into account, such as building height and orientation of the buildings and things like that. But we had to start somewhere. Next slide. And so this is just the some of the data that came from the Climate Central model. And so they have urban heat island effect data from sample sites right across the country. And you can see they're focusing on census tract. And it has particular applications, which I'll get into later. We decided to have more of a raster-based approach so we could have kind of a more fine-grained analysis. Next slide. But I will give Climate Central a nod. They've really done a lot of great pioneering work. So this is just a quick snapshot of the FME workflow in terms of reading the surface type and blue-green areas and then building essentially raster grids out of those that we can then model to build an urban heat island effect index normalized from 0 to 1 that we can use to do our heat island modeling in the northern Manhattan area. Next slide. So on the left, you can see we had this New York City open data, and that gives us a surface type, asphalt, grass, brick, what have you. And there are different estimated average albedo values. We got some of that from a couple of different scientific papers. And the nice thing about this, I mean, yes, a more generic approach would be by remote sensing, but because we had this high resolution data from New York City, we felt that this gave us a bit of a leg up. We don't have to do the satellite imagery interpretation. So you could feed imagery in at the same point for a larger area. But if you have this kind of high resolution local data, that's so much the better because, clearly here we can model individual paths and that might not show up from satellite imagery. Next slide. Ultimately, this data was then converted to raster imagery, or not, sorry, raster grids, not imagery. And so we had an albedo grid on the top left, and then we inverted that to come up with an absorption grid because absorption is proportional to heat. And then we also multiplied that by a cooling grid to kind of model the cooling effects of blue-green areas. And then we normalized everything from 0 to 1 so that we could then scale by observed temperature ranges. Next slide. And so this is the basically urban heat grid, observed heat island temperature range estimate for the northern Manhattan area. So you can see the north end of the park is that blue-green area, and then some other areas are very hot. So this is kind of an estimate for sometime late afternoon. And next slide. I'm just about done here. So the idea here is that grid, though there's a time series of grids, we consider that analysis ready data because it could be used for a number of different applications. In this particular case, we're using it to feed a localized urban heat alerts. And so what we do is we basically take that analysis ready data at the top, or sorry, I should say we have a web client or a mobile client which registers its location, We take that location, find out the weather using the National Weather Service from NOAA, the Weather Service API. We query what the forecast temperature is for that location. And then what we do is we query the Urban Heat Island OGC API service to find out what the urban heat island effect is for that location. And so then we can basically sum those together. We also account for humidity, multiply by that, and generate a warning. So then we have warning thresholds and alert thresholds, that can be calibrated. Ultimately, then you get a localized alert if those thresholds are exceeded. Next slide. So if we can just play this movie, it's fairly simple. These are just these grids. They're like, I think about a 5 to 10 meter grid. And you can see over time the temperature warming up in the artificial or built up areas, and they remain relatively cool in the park areas. Next slide. And what we did was we took these grids and gave them to another partner, Navteca. They imported those and used gaming engine to drape the temperature on the buildings and then apply a solar insulation, like a solar exposure model and shading. So just to build sort of a realistic 3D visualization. And that can be very helpful as a communication tool with the public, where they can say, oh yeah, that's where I live. And that kind of makes sense as to how hot it feels late in the afternoon. Next slide. And in the interest of time, I'm gonna I'll go through these weather alerts and then I'll skip over the 3D building stuff because I think HSR is going to cover that. So this is just a quick snapshot of the Weather Service API, the JSON message. Next slide. So that's one of the services we depend on. And this is just on the output side, some of the heat alerts where, near the park, we've got a estimated urban heat island effect, inclusive temperature of 82 Fahrenheit. And then outside the park in the built up area there, it's about 8 or 9 degrees warmer. And we even put some locations in there for closest cooling centers and other resources. Next slide. So yeah, all I'm going to say about this, actually, we'll go next slide. So basically what we did is kind of have a 2.5D approach to coming up with a rough estimate based on shade models from surrounding buildings, how much of a particular building is shaded using some trigonometry. And then once you have a ratio of shade, if you know what the total population of that building is, you could estimate how many people are going to have higher interior temperatures based on sunlight exposure. Next slide. Yeah, I'm going to skip through this in the interest of time. Just doing some of the math on estimating. So just kind of adding the 3D aspect to this analysis. So I'm going to wrap this up because I know we're a little bit tight for time. And anybody has questions, say on the 3D stuff, I'm happy to take that if we have time in the Q&A. But just to wrap up, currently most weather alerts don't yet include urban heat island effects. And I guess you could also say other weather alerts for other hazard types like flooding. You'll get a sort of a generalized, maybe at the large neighborhood level, but not so much at the building level in terms of flood hazard. Urban heat island effect models can support much more accurate localized heat hazard warnings. So I think we kind of demonstrated that in the pilot. If you're using the right input data, you can kind of use that pan sharpening approach where you take forecasts and apply it to high resolution input factors, other input factors to kind of get more accurate estimates. And we happen to be using FME to do this data integration. There's probably other platforms that you can do it. And the ultimate goal there is kind of adding that real-time factor for current estimates and also future scenarios, taking into account projected climate change impacts. And ultimately, our goal there is to kind of have an urban digital twin to promote resilience. I talked a fair bit about analysis-ready data. So the goal there is not just to provide a pretty picture like you see on the right, or heat alerts. But if you have well-designed analysis-ready data that integrates, like I was mentioning, this normalized index from 0 to 1 of urban heat island effect, it can be used by a number of different downstream analytic tools. We'll hear from HSR.health about the health impacts. It could also be used by AI and for cumulative impact analysis. One point I'll make about that, that's kind of fundamental that we found in this and other pilots, is you have to think about what your fundamental data unit is. And so if you're looking at census block, and that's the fundamental unit that hospitals need to figure out their ER loads, that's totally fine. And that's kind of the data model that Climate Central used. For us, we wanted more fine-grained alert resolution to support localized alerts at the building level, and that's why we chose a raster grid. So you have to think carefully about your analysis-ready data, what kind of data model. And ultimately, we would need more local observations, could be IoT coming from HVAC systems on the roofs of buildings, or other types of citizen science that Dr. Green mentioned. So yeah, I think there's a lot of potential here. The data is around, and it's just kind of, as David mentioned, how can we bring this together? And I think if we kind of can collaborate more, the sky's the limit. There's lots of ways that we can model some of these effects and then also provide feedback to support better policy and planning. Thank you.
Thank you, Dean. I think you really picked up the baton from David and carried it forward. It's remarkable to think that we could be modeling hazards across the country or across the world on a precision basis, that we now have the technology and the data to start to do that. You've certainly shown the way with your presentation. And our next presenter is Ajay Gupta, who is founder of HSR.health, a health consulting firm, who has modeled, has taken basically Dean's data about where the heat is, whether it's on a roof or on a facade or on the street, and turned it into how many lives that extreme heat is going to affect. So Ajay, please take it away.
Thank you, Alan. And thank you to everyone who made this possible. And Terry, Danielle, and everyone at GPN, and to others on our extreme heat team that Alan put together. So I'll be brief. Heat is a big problem, as has been covered by others, and this audience likely knows. It's why you're here. Let me do some brief specifics. Next slide, please, Bandana. Heat exacerbates many, if not all, known health conditions. Chronic conditions, of course, it leads to heat stroke, as you would anticipate, but it also increases the risk of interpersonal violence and mental health issues. This may not be as obvious, but I think anybody who's been trapped in a very hot area for some time knows that it does weigh on us in a different kind of way. And as has been mentioned, the problem, however, of heat is one that can be better managed with better risk prediction. If we know it's coming, we can do something about it. That is our specialty. HSR.health is a health risk prediction firm. Our goal is to say today what health risks will be impacting an organization, a community, a business, or a hospital tomorrow so that we can mitigate those risks. Next slide, please. What we're building here is a solution that works in all environments. This initial pilot in New York was, of course, urban, and we've been talking a lot about urban heat index, but we sometimes forget we still have 70 million people living in rural environments. And another thing that we often forget is that many of our assets as a nation are actually in our rural environments, our farms, ranches, and the research labs, and a lot of assets are there that we need to protect or want to protect as well. We're actually modifying this urban heat health risk index to cover rural and suburban areas. But the goal remains the same, that we want to be able to give everyone information on what the heat risks are so that they can take preventive actions, whether that is responding to people at risk or that is designing the built environment in a way that minimizes the exposure to heat risks. Next slide, please. Health response is typically reactive, not just at an individual person level where we sort of do something to protect ourselves once we get sick, but also at a systemic level. So this is Northern Manhattan, where we did the pilot, and EMS is in community districts 9, 10, 11, and 12. They respond when they get a call. They don't necessarily pre-position assets to know where to expect. Next slide, please. Our heat health risk index can give EMS and hospitals and community service organizations information on where to anticipate the highest number or the most critical cases of heat stroke or heat-related health conditions, so they can know where to respond. Bandana, can you skip a few slides down to, because they've been covered, down to, next slide, please. Next slide. One more. Yeah, just briefly, I won't talk about it, but those who are interested can read through and look at our workflow. I'm happy to discuss it at leisure. Next slide. We did, as we did this project in New York, look at past heat waves in other cities to see what may happen. Chicago, where you can see a death spike. Next slide. France, which is part of Europe, of course, where they typically are a cold environment, right? So kind of a cold continent. So they really do not have a built environment designed to reduce the impact of heat on buildings. So you can see they've had, and the news covers how they have a great deal of challenge with summer heat. Next slide. We looked at Vancouver as well. Next slide. And then just quickly to show, the next slide, please, the results of our study in Manhattan, which I think is, as Dean mentioned, it's a pilot. So we knew we didn't take every bit of information into account, and we knew that some of the assumptions are not assumptions we would make if we were doing this, professionally implementing it. But we did address the number of people impacted in 2 scenarios, one with a 5-day heat wave and one with a 5-day heat wave and 2 days of blackout, meaning we lost power towards the end of the heat wave, and assess the total number of people impacted in the area and the potential hospitalizations that may come. You may see that the hospitalizations in the more aggressive scenario, scenario 2, and deaths did not rise that dramatically. And a lot of that is because of how we assess deaths in America currently. This is being revised by the CDC when the CDC is open. But in the past, heat has just simply not been as large a consideration. So death certificates don't always take heat into account. As that changes, we'll get better numbers, if you will, and perhaps more accurate numbers of what the death rate due to heat directly may be. Next slide. Here's something that we found in our research, again, with all the caveats to the research was a pilot, but it does appear that there is a threshold temperature at which both hospitalizations and deaths can rise substantially, which indicates actually in a reverse way, it's good news in that we kind of know where to take advantage or to mitigate against heat in all neighborhoods. Next slide. Next slide. I won't read it, but our sources are here. There's an engineering report of our work where you can look at sort of how we got the data. Next slide. There are data that challenges, as I want to mention, and as Dean covered, the temperatures that we hear reported for the city are not necessarily the temperature you're exposed to where you're standing. And that makes a big difference, especially if we are among the most vulnerable class, people who maybe have a heat-related condition or people who can't avoid being outdoors. One use case that I want to mention because it impacts rural areas, maybe a bit more than urban areas for whatever reason, are youth athletes. Often, especially now in football season, if you practice outdoors for hours at a time and you kind of have to do that, that's kind of the only kind of place to practice. So while they may be in socioeconomic district, they're young people, but still, if you have no way around exposure, there's a risk. And so knowing the exact temperature you're actually exposed to is kind of more important. Next slide, please. There are a lot of countermeasures and next slide, please, that organizations can go to. I saw in the chat, green roofs are certainly a part of it. Making the built environment more like the natural environment is certainly part of it. Next slide. There are also personal countermeasures that we can try to undertake. You know, if heat is a problem, immersing yourself in water for hydration is potentially a solution. That could mean going to swimming pools, taking frequent showers, and that kind of thing. Staying in vented indoor spaces away from direct sunlight, if that's possible. Protective heat clothing can be helpful for some, as you know, that is a ancient kind of remedy for the extreme heat. Cold compresses. Finding places indoors that have good air conditioning, like malls and museums, is certainly a good idea when and where those are conveniently available. If you have to take a long bus ride to get to the museum, that may not help in the nutshell. Next slide. So since the pilot, our firm has been working with a couple of counties, rural counties across the country, where we're building the expansion or expanding from urban to rural environments. So we cover urban, rural, and suburban environments. That's kind of an important, I think, expansion. Next slide, please. And I do want to spend a moment just showing still images of the dashboard. Happy to talk with anyone afterwards on a more expansive demo of the dashboard that we're building. This is an application that allows users to see the heat risk in their community. This is showing the pilot area and showing high risk through low risk and extreme high risk areas, both with respect to the temperatures and all of the things around the felt environment and urban heat island effect, as well as the risk to the population. So if you have a very hot area, yet very healthy people, that may actually be lower risk than a not quite so hot area, but a lot of at-risk individuals, right? So that's the kind of risk posture that we're developing. Next slide. We are also showing the built environment because that impacts not just the heat, but where and how solutions can be built. So this is a map of the schools in the area, and schools are often a building that can be converted into a cooling center because the government already has access to those facilities. They typically may have good air conditioning, or at least the government has access to update the air conditioning in those buildings. Next slide. We also show the socioeconomic data by risk level for the area to help assess the risk level. Next slide. And this is for the highest risk area is in the pilot. Next slide. As we also show the economic risk factors. One thing I want to make clear is that there may be costs spent on addressing heat, but mitigating heat should have a positive return on investment through reduced healthcare spending, through improved workforce productivity, and increased economic activity. If people are feeling too hot, often they don't go out, they stay in their homes or apartments, which often leads to needing hospitalization. All of those things are lost economic opportunity and increased expense by having, filling up our hospitals. So the heat spend or heat mitigation spend should be a positive ROI in the actually quite near term, because these heat waves last for 5 to 7 to 10 days. The monies spent in those periods should be positively received economically in the near term. Next slide. We're also building a generative AI front end, because OpenAI has shown us that everyone knows how to use a chatbot to do advanced analytics. And also it gives the information directly to decision makers. And if we were to deploy this for a county or a city or some organization, they have the choice to make the information available directly to citizens so that they can know a little bit better how to predict heat effects for them and protect themselves. Next slide. And finally, I would just like to say, we are working to be able to deploy this by summer 2026 in your communities and have your users trained so they can use a solution to help mitigate things ranging from understanding which hospitals in a city may be at greatest risk of being surged by heat stroke and heat exhaustion, to which communities may want to help their schools, high schools and middle schools, readjust their practice schedules to avoid heat stroke for our kids. Thank you, and back to you, Alan.
Okay, Ajay, thanks. And I think, again, this is remarkable because not only can we find what the heat will be in urban spaces or rural spaces or suburban spaces to the building, or even to smaller, granular, precise levels of demarcation, but we can also anticipate the numbers of people who might possibly die or be sick from a number of different factors that heat makes worse. This is a level of precision and understanding of how a disaster can affect a local government I don't think we've seen before. And congrats for doing this. I think it has many applications. I'd like to move on to Dr. Bandara Kaur, who has worked with the Department of Energy, may still be doing so. She will talk about one of the critical factors for keeping deaths down in extreme heat events is the availability of air conditioning, among other things. And she will talk towards, among other strategies, what we need to do to make sure that electricity continues to be reliably delivered during periods of time when there is the most stress on the electric system. Because the last thing you want in an extreme heat event, when people are depending on air conditioning to keep them within a living zone, is for the power to go out. And the air conditioning not available and the heat rising in the residential spaces where most people die during a heat event. So Bandara, take it away.
Thanks, Alan. Thanks, David, Dean, and Ajay for setting the stage. So far, we have discussed about what is urban heat island and what are the implications of extreme heat events, how to model them, and also there would be discussion how to communicate that information to help with preparedness. As Alan mentioned, we need to understand the role of energy because we do need energy for the continuation of emergency and essential services and what we need to do. And I saw some chats and in Q&A about air conditioning and other stuff. Often we don't think about it, but extreme heat and energy, they do interact with each other in the sense extreme heat causes the increase in cooling demand, and as we increase the use of air conditioning, we end up causing the urban heat island effects because of radiation. At the same time, extreme heat also can burden the energy grid and reduce the supply as well as the transmission efficiency aspect of it. And combine that with increased cooling demand can cause power outages and or your strategic brownouts to minimize to balance out the supply and demand situation. And we can expect the situation to worsen because of increase in data centers as well. That is going to burden the grid. At the same time, the increased heat your energy usage can be a burden for certain communities, as I had gone over, those who might be vulnerable and they may experience adverse health impacts. And extreme heat also costs about 100 billion in lost labor productivity. So there is a socioeconomic aspect to it, and we need to understand what we need to deal with to address the energy requirement. As you can see, from 1973 onwards, there has been an increase in number of cooling degree days across the in CONUS, actually 48 states plus DC. At the same time, as you can see, the electricity usage has gone up from almost 700 kilowatt hours per person to now about 1400 kilowatt hours. We have doubled. Not necessarily we have that energy generation capacity to meet that increased demand, and that often leads to some of those brownouts to address the supply demand aspect of it. If we don't do that, then the cost of energy can go up for certain communities, and you can go through news articles about ERCOT, how it was dealing with rate pricing a couple of years ago because during the summer time frame, and some households had to pay $1,000, and that probably is not the rate at which you started out using your energy. This also shows, based on the 2020 Residential Energy Consumption Survey, which is done by Energy Information Administration, and the rate of AC adoption across the US. And we have about 90% of the households have air conditioning. It could be a single unit or a split unit or HVAC systems. But as you see, where on the western part of the US, it is about less than 73%. The survey also shows that currently about 10 to 12% of the US households don't have an air conditioning. It's about approximately 39 million households. If any of them are in the lower income strata, then imagine their situation during summer months, and they have to think about how to deal with their health and the energy demand without increasing the cost burden of it. So this is another study that was done to explore what happens to buildings with poor insulation, which could be the case with many communities, how they react during a heat wave concurrent with an outage. Definitely in those houses, they have high heat risk for households living there. We recently had a study done and we published it using data from outage data that was captured through one of the platforms maintained by Department of Energy Eagle Eye that has outage data from 2014 onwards. And we explored the relationship of heat wave driven outages. Generally, heat waves alone can increase the frequency and duration of outages because of increased demand. But if you have a compound event like Hurricane Laura or Hurricane Beryl last year, when the hurricane is happening and you are concurrent with a heat wave, then there is a power outage. Imagine the cascading health impacts on some of the households. And if we have longer heat wave, then greater is the impact on electricity supply. So what can we do, and what DOE has been supporting some of these activities at the building level, because that's where we spend majority of our time. We can do active cooling, ACs, fans, HVAC, and phase change materials, and responsive ventilation systems. We can have also passive cooling, which is probably little affordable as opposed to having ACs and HVAC systems, which may not be affordable for certain households, is to have reflective surfaces, and also addressing building code for insulation and air tightness, and having triple pane windows, which is expensive, not everybody can afford it, and thermal mass. At a city level, you can have nature-based solutions like green infrastructures and built environment interventions like cool pavements and energy-efficient buildings and resistant materials. Planning measures are another solution. At a community level, you think about cooling centers. We have done a study to explore the cooling center aspect in different places across the US. Not necessarily everybody has access to cooling centers. At the same time, cooling centers may not have the any of these cooling solutions in place as well, and community preparedness and infrastructure solutions. At the same time, these are some of the studies that DOE has funded to improve thermal resilience, which is a building's ability to maintain indoor environment that is comfortable for your daily activities. And the metric used is passive survivability. Through building code, we have some projects, like I said, these are DOE funded projects where they actively work with through the North American, the state energy offices, through state agencies, to improve the building codes both for new buildings as well as retrofitted buildings to address their thermal resilience and passive survivability. These are, here are the publicly available documents and information that you can access, and I would be happy to answer questions afterwards. And improving energy resilience. As we move away from the building to a community or a facility, there are strategies that could be in place, like having microgrids or green infrastructures, or a combination of microgrid, green infrastructure, and building code solutions to, again, address the availability of energy during extreme heat time frame, so you can continue to have your critical loads and essential services. And again, these are some of the studies where the labs, I am at the National Energy enrolled the National Renewable Energy Lab. We work with communities and give them technical assistance other than doing R&D to develop different solutions. I think now handing over to you, probably.
Thank you.
Thank you.
Thank you, Bandana. And I would just like to emphasize here, one of the things that the Open Geospatial Consortium has been working on for 8 years now is developing a data model for underground infrastructure or infrastructure in general, including electric systems. So what the presentations up to this point have pointed out is the critical importance of making sure there's a consistent, reliable supply of energy for air conditioning during times of extreme heat. Otherwise, the risk of casualties is just enormous. And so that would be probably a recommendation, which is to really know that you've got in your jurisdiction a resilient electricity system that will supply even under stress, and even with the AI centers drawing away so much power. Uh, I will just briefly say here about the citizen science end of it is that as we get to know the numbers of people who are at risk during an extreme heat event, either with electric still supplied or when the electricity goes out, uh, we know that in a major disaster, one of the first things that goes down is the 911 emergency response system. Because if you have a community of 100,000 people who are experiencing heat stress and they're calling 911, there is no way there can be response. So another Open Geospatial Consortium project that I worked on with others, including a team from Manitoba, was the use of mobile phones, sensors embedded in those phones, artificial intelligence, and a response community that also can talk to people who are at a moment of stress or danger for them, needing to communicate with the responders. And if you go to the next slide, so a very creative team from Basel Labs, are you going to the next slide? Hopefully you get there. Uh, has developed an end-to-end system. It's still in pilot, which can actually digitize spoken speech. It can translate speech into a common language or written speech into a common language. It can categorize, analyze, and rank words and phrases at a time when you can't reach a 911 operator. It can distill meaning in those communications. It can geocode the location of anyone making a call. It could do cluster analysis for the emergency management team, and it can prioritize by a location basis who is at greatest risk at any particular point in time. So these are technologies of the future. They use Geo AI agents to do the analytics, and they would be better than not being able to reach anyone at all. And they can automatically connect you to local responders who can help. So this is something we're continuing to work on, and hopefully there are potential solutions right now if you're interested. Next step, next slide. I think I'm pretty much done. Oh, this is just to illustrate the fact that more and more personal sensors are coming out and being made available. They can be integrated with your smartphone or communicate with your smartphone from a perch on your couch or your windowsill, so that no one need to be unknown if they are suffering during this kind of an event or any kind of disaster event, should 911 not be available. There's a workflow here, again, to monitor people's health, to identify, diagnose, locate, and rank individuals, to get that information to a responder, and to keep the overall disaster manager informed about everything that is going on in households across a disaster area. So this is coming. It may not be for a couple of years, but this capability exists today and just needs to be implemented. Next slide. Okay, so where do we go from here? What we have shown you is known or exists, so that it's a matter of who is really interested in moving forward. We know the solutions can be created. We need the financial means to advance this work, obviously. We need to involve all the professional groups that are interested in helping people during disaster events. And we need to develop mature, cheap, reliable applications that can be readily distributed and used by local, state, tribal county governments across the country and maybe across the world. Next slide. Or is that the end? No, I think that's the end of it. We're done. So I think I've left 10 minutes for discussion. Oh, next steps, of course. You can write to me. Go back to the previous one, because if you have any questions or comments that you would like to make about this presentation, please send a note to me at leidnera@nyc.rr.com, and we will try to get to answer your question. We need to develop specifications and a plan for the 1.0 version of an extreme heat prediction workflow. We need to find the necessary resources. The goal is to have a working prototype of an end-to-end solution by the summer of 2026, with Ajay referred to. And the vision is to also develop, using this kind of analytic framework, methodologies to address other disaster types. So with that, we're done, and we have some time for questions.
Thank you, Alan. We did have several questions that were coming through the Q&A, and our speakers have been diligently answering them in the background. So really appreciate you guys while you weren't speaking by answering those. So those should be available to the speakers. I know several of you answered some questions. I didn't know if there were any that you wanted to bring back up to the group for further discussion. This is to the panelists.
I can just highlight a couple of, I just dropped a link to the blog that OGC recently published on this. I guess it was late August. So that's a couple links back in the chat, but maybe we can add that to the tail end of the deck before it goes out.
Yeah.
So that's a good summary of the project.
And there was a question by Andrea Perez that I hit the wrong button, but she asked about data for rates of asthma and COPD, et cetera. And there are a lot of data on health considerations at the local level that are available through CDC Wonder and CMS and other data sets. So I don't know if Andrea has checked those already for her region, for her area. But those are good starting points, and certainly happy to discuss offline other data that we have access to for health considerations at the community level.
I want to throw out here just the notion that at this particular point in time, GIS professionals as a community are more networked and more connected together than we've ever been before. And we're talking to each other through our organizations like GPN, through the GIS divisions of National Association of Counties and National League of Cities, NYSGIC, the tribal councils, and others, and NAPSIG, obviously, so that if we can develop a solution for one that's adaptable for all, we now have the networks to distribute those solutions so they can be adapted for each local government as needed. At least that's the hope. But the potential exists because really we are all now, like never before, talking to each other.
Yeah, you raise a good point, Alan. None of us, there's lots of data out there, but none of us are going to solve all this on our own. It takes collaborative effort. I think, kudos to OGC for hosting some of these pilots. And so I'd encourage people to get involved with groups like OGC if this is something of interest. But yeah, there's all these other professional groups like the Geospatial Professional Network that kindly hosted today. And yeah, I think that really is key, combining, these kind of collaborative networks with things like open standards so that we can do the kind of data flows and analytics to support solutions in this space. And I did want to say kudos to Alan as well, just for kind of bringing all of us together on this one. It was definitely a fun project.
Well, kudos to you all for agreeing.
Do we have, yeah, any other questions that came up?
I think it was an interesting question that Chris Rogers asked, or Christopher Rogers asked about the first step. I mean, that's, yes, most local departments may not have dedicated GIS staff. And even if they do, the data that we talked about today is many factorial, right? So that's why we're using a generative AI front end to sort of remove one level of complication so the decision makers can get data quicker, or citizens can get data quicker. And as Alan said, the goal is that we can have a solution live by summer of 2026.
I really think that if you look at the presentations and you look at the potential uses of AI to support solutions that solve the problem for thousands of jurisdictions, I think here you see the real power and potential of AI, not necessarily in generating term papers, but actually being a key tool to be able to address problems that exist on a massive level, which human agents just, there's not enough of us, or nor the time in a disaster to really respond. And you need that automation that I think only AI will be able to provide to be able to do those things.
I would also add that in the discussion, I think often we forget about the energy aspect, and that's why I mentioned think about the state energy offices that you have to go and talk to them, because some of the AC and code changes have to happen at that level, where the building code, where the land use changes have to happen. Your urban design requires approval at there, and the green infrastructures. So while we can mitigate the health impacts, without energy, it's not going to happen. And AI definitely is a better way of automating and manipulating a large chunk of data. Keep in mind, with AI also requires a lot of energy. Therefore, what is the trade-off that we have to live with? Do I want to automate the process, or do I need energy to cook and remain cool in my house? And what is the trade-off, and who decides that is up to the users, the communities on the ground, and the professionals who are dealing with it. I have shared my email and LinkedIn, and would be happy to talk about the different work that has been funded through DOE, NSF, and other entities in this space to help communities improve their resilience to different extreme weather events while ensuring reliable and affordable access to energy during the and before and after the event.
I just wanted to come back again to hoping people recognize what we had to do in this pilot is that the people who came into this are from different disciplines: energy, health, observation, GIS. And so what one of the takeaways as you kind of leave this talk now is think about, do you have that team of partnerships? Do you have that collective group? Because what we piloted here was, is it possible to even bring these different pieces together? And I think we proved yes. But it's not always easy for people to find those other partners in communities they don't usually work with. We were fortunate enough that OGC and many of us have known each other for years to be able to reach across the different sectors and disciplines. But if those on this call or on this webinar are interested in, hey, I've got elements of trying to put this type of group together. We'd like to kind of tackle this type of problem. Reach back to us. And we've learned that it's not just the data and it's not just the problem, but it's really creating the right partnerships and concentrating on the right kind of outcome. And so hopefully we've given you an idea of how to build this type of capability, the type of different perspectives that are needed. It's kind of a consortia idea, partnership idea. And there are some similar groups that have been doing this, from health, water, wildfire, insurance. But think about where you are in the communities you've worked with. And we'd really like to hear back from you to say, hey, I think we could put this group together to make some progress in this geography or over this time frame. And I think that would help us move some of these next steps forward.
And if I could just add to that quickly, David, I know we're pretty much at time, but One thing we found with the series of disaster and climate pilots at OGC is, and others have mentioned it, you've mentioned it, it's key to get key stakeholders and domain experts involved so that we can kind of calibrate what we're doing. Because I noticed one of the questions on AI, like what are the risks associated with AI? And one of those is you can get into all sorts of hallucinations. There's a lot of power in AI, but it needs to be calibrated. And in many cases, some of these models that we looked at are very deterministic. So in that case, you have to kind of be careful. If you've got a deterministic model, you don't necessarily need AI for that piece, but AI can maybe help you with some of the cumulative effects or integrating across disciplines. Yeah, so when you keep stakeholders and domain experts engaged, that helps you kind of sift through what you're getting back from AI and figure out, well, what's relevant and what's not.
Yeah, the take-home message, Dean, is AI is just a tool dependent on what
Yeah.
I'm giving it. Don't think the AI is the panacea to all the problems.
Magic wand.
Yes, that's not the case. So we just have to be aware of how we are using it, the purpose behind it, and what is being used to analyze everything, or else we are responsible. Thanks, everyone.
Yeah, thanks
Thank
everyone
you.
for your time.
Thank you. If only AI solved all of our problems just like
If
that.
only.
We have just a couple like final announcements and resources that I wanted to be sure to share with you all as we wrap up. So first, thank you, Alan, David, Dean, AJ, Bandana, for doing this type of research and analysis and showing the power of such a collaboration. And then again, just synthesizing your great work and providing more of just the practical applications for communities to address and combat extreme heat. So we do have, I don't know if you can show the last couple slides, Bandana. We have a couple of events coming up that I don't think you'll want to miss. I want to make sure you're aware of those. There will be on the screen in a second a QR code where you can go and just click all of the webinars and upcoming meetings. We have almost there coming up. So we have a few conferences coming up that you won't want to miss. You can go to the next slide. If you haven't heard, GPN has a learning annex, which has a ton of previously recorded webinars, certified workshops that have been updated to on-demand courses, conference proceedings, and more. And you can earn certificates of completion for use for GISP education points. And GPN members can access that content, either some of it's free and some of it's at drastically discounted rates. So definitely something for you to check out. And finally, just thanks so much for attending today. I don't know if there's one more slide or not, Bandana. And for the speakers for their time. The Climate and Community Resilience Committee tries to put on these informative webinars, and this was certainly one of those. So thanks for the speakers. Thanks for attending this webinar. You can find out more about us by going to the GPN website, going to committees and work groups. You can see our committee, you can see others and get involved. There's also a link on our experience builder for how to join. We hope that we'll see you again back next month for our Portraits of Resilience webinar for our November series. With that, I hope you all have a wonderful weekend ahead. Thank you for being so engaged to our audience and our speakers throughout this whole session. And we hope to see you again next time. Enjoy the rest of your day.
you, everybody.
Thanks, everybody.
Bye-bye.
Bye.